So in this video, we're going to continue with CC13, which is groups of the periodic table. Again, this is a paper 2 topic, so it doesn't come up at all on paper 1. And this is going to be the first of 2 videos on the halogens, which are in group 7. So if we look at a periodic table, we see that we're going to be looking at fluorine, chlorine, bromine, and iodine, and also a little bit at astatine. Just to remind you that elements are put in groups based on their physical and chemical properties. Again, when I say chemical properties, I mean how they react. So if they're all in the same group, as the halogens are, they all react in similar ways and they all have similar physical properties. We're going to start by looking at those physical properties. So the halogens, being on the right-hand side of the periodic table, they are non-metals. Because they're non-metals, they share properties with other non-metals, such as the fact that they are poor conductors of electricity. And by that, I just mean they don't let electricity pass through them. Unique to the halogens is the fact that they are toxic and corrosive. By corrosive, I just mean that they can burn through your skin. As well as knowing these kind of general physical properties of the halogens, you need to know the color and state of chlorine, bromine, and iodine. So if we look at this table here, you can see that chlorine is green, bromine is brown, and iodine is purple. And looking at state, you're going gas, liquid, solid. I've included fluorine and astatine in the table as well, because even though you don't need to learn their colors off by heart, you're expected to be able to use the trends in the physical properties to predict the colour and the state of fluorine and astatine. If we look at colour first, you will see that as you go down the group, the colour is getting darker. So you're going from green to brown to purple. Therefore, if you were asked to predict the colour of astatine, you would need to say a colour that was darker than purple. So the obvious answer there would be to say black. If you were going the other way, you would need to say a colour that was lighter than green for fluorine. So you could say, I'm just going to say colourless. With state, you can see that you're going from gas to liquid to solid. That tells me that the boiling and melting points are increasing as I go down the group. So for example, if chlorine is a gas at room temperature, then that tells me, okay, your typical room temperature is 25 degrees Celsius. That tells me that 25 degrees Celsius is a high enough temperature to turn chlorine into a gas. Whereas for bromine, it's a liquid at room temperature. 25 degrees is not enough to turn it into a gas. And iodine isn't even a liquid, so it's still a solid at room temperature. So the melting and boiling points are increasing going down the group. Therefore, if iodine is a solid at room temperature, I would also expect astatine to be a solid at room temperature. And if chlorine was a gas, then fluorine must also be a gas. So you do need to know the colour and state of chlorine, bromine, and iodine, but then you need to use this data to predict the colour and state of fluorine and astatine as well. Remember, they get darker as you go down the group, and melting and boiling points increase as you go down the group. That all counts as physical properties, but we also need to look at chemical properties. So because the halogens are all in group, before we look at chemical properties, we need to look at the test for chlorine gas. This is a 2-mark question, and to get your 2 marks, you need to tell me that you would use damp blue litmus paper and that the litmus paper would turn red and then bleach white. So it's just a test to use to confirm that the gas is chlorine, just like we use the squeaky pop test to confirm that a gas is hydrogen. Something you just need to learn off. It's for 2 marks if it comes up. Okay, now we're going to move on to the chemical properties of the halogens. Remember, chemical properties relates to how they react. And if we're looking at chemical reactions, we're always going to be looking at electrons. So because the halogens are all in group 7, they all have 7 electrons in their outer shell. They want to have 8 electrons to have a full outer shell, which means they all need to gain 1 electron. To gain 1 electron, they can either react with metals or react with non-metals. The first reaction we're going to look at is the reaction between a halogen and a metal. So lithium, we've seen lithium before, it is a metal, it's in group 1. And then chlorine is your non-metal from group 7. Metals always want to lose electrons. Because lithium is in group 1, it's got 1 electron in its outer shell and it wants to lose 1 electron. Chlorine wants to gain 1 electron, which means lithium will transfer its electron to chlorine. When it does this, lithium ends up with a full outer shell and a positive charge, and chlorine also ends up with a full outer shell and a negative charge. Because this reaction is taking place between a metal and a non-metal, I can say that this is ionic bonding. So lithium and chlorine bonding together, that is an example of ionic bonding. Chlorine, or indeed any of your halogens, can react with any metal. Okay? Metals always want to lose electrons, so the halogens, who want to gain electrons, are willing to react with any metal and to form an ionic bond. As well as reacting with metals to gain electrons, the halogens can also react with non-metals to gain electrons. The example I have below is an example of two chlorine atoms reacting with each other. So again, each chlorine atom wants to gain one electron, neither of them want to lose. In order for them both to have a full outer shell, they need to share electrons, and I represent this by drawing the two outer shells overlapping. This space here in the center represents the shared electrons. To know how many electrons to draw in this sharing section, you need to look at how many electrons each chlorine wants to gain. If chlorine wants to gain one electron, then it will share one electron, so I'm going to draw one cross in the center. The other 6 electrons that chlorine has, it will not share, so those 6 electrons are drawn on the outside. Just make sure that you have only drawn 7 crosses in total. Chlorine's only got 7 electrons, so I should only have 7 crosses drawn. The other chlorine is exactly the same. It wants to gain 1 electron, so it will share 1 electron. And the other 6 electrons, it will not share, so they will be drawn on the outside. Again, I'm going to double check that I've only drawn 7 dots in total because chlorine only has 7 electrons. If I look at each chlorine atom, I can see that each chlorine now has 2, 4, 6, 8 electrons and 2, 4, 6, 8 electrons. So by sharing, each chlorine ends up with a full outer shell. Because chlorine is a non-metal, when the 2 chlorine atoms bond together, this is an example of covalent bonding. All halogens will react with each other. So chlorine atoms will react with each other, fluorine will react with each other, iodine will react with each other. And the reason they do this is because when they react, they end up with a full outer shell. We call these diatomic molecules. The di means 2 and the atomic means atom. So you've got 2 atoms in the molecule. Halogens always exist as diatomic molecules because when they pair up, they end up with a full outer shell. So rather than existing as individual atoms that don't have full outer shells, they pair up and they form diatomic molecules because they do have full outer shells, and that is more stable. As well as reacting amongst themselves, the halogens can also react with other nonmetals, and a classic example is the reaction of halogens with hydrogen. So the halogen I've chosen is again chlorine, and I've drawn it with 7 electrons in its outer shell. Because it's got 7, it wants to gain 1 for a full outer shell. Hydrogen only has 1 electron. Remember, its outer shell is going to be the first shell. So if it gains 1 electron, it will have 2 electrons in the first shell, which will be a full outer shell. Because they're going to be sharing electrons as they both want to gain, I'm going to draw the 2 outer shells overlapping. Chlorine wants to gain 1, which means it will share 1. Its other 6 electrons it will keep to itself, so I'm going to be drawing 7 crosses in total. Hydrogen wants to gain 1, so it will share 1. It doesn't have any other electrons, so I'm not drawing any on the outside of hydrogen. Hydrogen ends up with 2 electrons in its outer shell, which is a full first shell. Chlorine ends up with 8, which is a full outer shell for chlorine. All of the halogens will react with hydrogen to form structures that look like this. HCl, hydrogen chloride, is a gas at room temperature. But you're probably more familiar with calling HCl hydrochloric acid, and we need to look at the difference. If it's HCl and it's a gas, then I call it hydrogen chloride. But if it's HCl and it's aqueous, aqueous meaning dissolved in water, then I can call it hydrochloric acid. This tells me that when HCl is dissolved in water, it can react as an acid, but when HCl is a gas, it cannot act as an acid. And we need to understand why. Acids always produce H plus ions. Okay, if it doesn't produce H plus ions, then it is not an acid. The fact that HCl aqueous is an acid tells me that when I dissolve HCl in water, it produces H plus ions. The fact that HCl gas is not an acid tells me that as a gas, HCl does not produce H plus ions. And we'll just look at this diagram here to explain that. So I've got HCl as a gas, and I've got a beaker here of water. When I dissolve HCl gas in water, what's going to happen is that HCl molecule is going to split up, and I'm going to get H plus ions, and I'm going to get Cl minus ions. If I took another HCl molecule, which would be a gas, and dissolved it in water, that would also split up, and I would get H plus, and I would get Cl minus. When you dissolve HCl in water, HCl splits up to produce H plus and Cl minus ions. Because it's producing H plus ions, we can say that HCl is an acid when it is dissolved in water. It's not just HCl that reacts this way. The other halogens all do the same. Hydrogen fluoride as a gas is not an acid, but if you dissolve hydrogen fluoride in water, it becomes hydrofluoric acid because the hydrogen and fluorine separate to give you H plus and F minus ions. Similarly, with hydrogen bromide, as a gas it's not an acid, but if you dissolve it in water and you have hydrogen bromide aqueous, then it is an acid called hydrobromic acid. The reason it's an acid is because that hydrogen bromine bond is going to break when you dissolve it in water, and you're going to produce H plus and B or minus ions. Remember, anything that produces H plus ions when dissolved in water is considered an acid, and all of your hydrogen halides will dissolve in water to give you H plus ions. We're just going to have a look at a couple of exam questions on this topic. So here you're given the name of 3 halogens and you're given their appearance. You're then asked to predict the appearance of astatine. If you look at your periodic table, you will see that astatine is below iodine. Going down the group, you can see that the colours are getting darker and you're going from a gas to a liquid to a solid. If astatine is below iodine, you would expect it to be even darker. So darker than grey would be black. And as the melting and boiling points are increasing, you would also expect it to be a solid. Another question asks you to estimate the boiling point of astatine. So if you look at the boiling points are increasing. So you're going from minus 188 to minus 35 to 59 to 184. You would expect the boiling point of astatine to be greater than 184. So if you pick any number that's greater than 184, you're going to pick up the mark. This question here asks you to describe the test to show that a gas is chlorine. Again, this is a 2-mark question. You'll get 1 mark for describing that you would use damp blue litmus paper. And then the second mark goes for giving the colour change. So first it will turn red and then it will bleach white. This question here, bromine reacts with hydrogen to form hydrogen bromide. Hydrogen bromide then dissolves in water to form a solution. Give a reason a universal indicator turns red when added to this solution. So we have seen that when you dissolve hydrogen halides, in this case hydrogen bromide, when you dissolve it in water, they become acids. So when they ask you to give a reason why universal indicator turns red, we should hopefully know that universal indicator turns red in the presence of an acid. So I'm going to write, give a reason when it adds the solution, that the solution is acidic. But more than that, I'm going to say why it's acidic. The reason that solution is acidic is because it produces H plus ions. That's what makes a solution acidic, because we've got H plus ions. Okay, so make sure you're mentioning the H plus ions when you're talking about it being acidic. The rest of the questions here on the halogens all relate to displacement reactions, which I'm going to do in the next video on the halogens. The next video on the halogens is really, really important. It's to do with their trend in reactivity and displacement reactions, and there are quite a lot of exam questions that come up on that. So make sure you watch the next video on the halogens, where I'm going to go through displacement reactions